Today we're going to talk about acid-base concepts. What's an acid? What's a base? And how can we identify them? Now earlier you may have learned a few characteristics about acids and bases, like acids taste sour and bases taste bitter and things like that. But we really want to look at the definitions of acids and bases from a molecular standpoint. So we're going to talk about three different ways to define acids and bases here. And the first one is the one we call the Arrhenius definition of acids and bases. Namely, an acid is something that increases the amount of H+ ions in solution, while a base increases hydroxide ions in solution. So some classic examples of acids and bases where it's easy to see why they are acids and bases by the Arrhenius definition. We've got HCl, and you can see that HCl will produce H+ in solution. You can see where that hydrogen comes from. You have acids like sulfuric acid, H2SO4. Again, you can see where the hydrogen ions come from. If you look at bases, classic Arrhenius bases are things like sodium hydroxide and potassium hydroxide. These are salts that have hydroxide ions in them, and so you can see that when you put them in water, they'll dissociate and there will be OH- ions in solution. But let's think about a very common household base, ammonia. We know it's a base because it neutralizes acids, and that is a characteristic of a base. But if you look at ammonia, you see that it does not have any OHs on it, so how in the world does it make hydroxide in solution? In order to understand why ammonia is a base, it helps to become aware of a very important equilibrium which exists in all aqueous solutions, which is basically the self-ionization of water. And this is basically where a water molecule breaks apart to form H+ and OH-. So you can think about what the equilibrium constant will look like for this. So you can see how it would have H+ and OH- concentrations on the top, and then water, of course, is a pure liquid, so that gets left out of our equilibrium constant. And this equilibrium constant has a very special symbol that we call Kw, W for water. And we know the value of Kw, it's about 10 to the minus 14th at 25 Celsius. So let's now look at how ammonia can be a base. If you put ammonia in a solution of water, some of that water can ionize and form H+ and OH-. And then the ammonia can grab onto one of those hydrogen ions, leaving an unpaired hydroxide ion. And so this is how we get hydroxide ions building up in an aqueous solution of ammonia. So ammonia does meet the criteria for an Arrhenius acid, but it's really hard to look at NH3 and say, hey, this is going to make OH-. And so we have a different definition of acids and bases from Bronsted-Lowry, where an acid is a proton donor and a base is a proton acceptor. Now, what does it mean, proton? Well, if you think about a normal hydrogen atom, it's one proton and one electron. So an H+ ion will just be one proton because it's missing the electron. So we often use the word proton to refer to H+ ions. Now, the thing about Bronsted-Lowry acid-base reactions is that they are reversible. So here is the reaction we were just talking about, and you can see that we have ammonia reacting with water to form NH4 plus the ammonium ion and OH- hydroxide ion. Ammonia here is the base because it's a proton acceptor. Basically, in order to turn into the ammonium ion, NH4+, it needs an extra H+. So it's going to take one. That makes it the proton acceptor. Now, where does that proton come from? It comes from the water, where water is going to give up one of its hydrogens and form OH- as a product. So because water here is the one donating the proton, that makes water an acid. And so what you will see is that for a Bronsted-Lowry reaction to happen, you need to have two things. You need to have both a base and an acid. If you have a base in solution, a lot of times the acid will be water. If you have an acid in solution, sometimes water will be the base that accepts that proton. I said these reactions were reversible, so let's look at the reverse reaction. In the reverse reaction, we have the ammonium ion reacting with hydroxide to make ammonia and water. Ammonium ion here is the proton donor. You can see it gives up one of its hydrogens as it turns back into ammonia. So then the hydroxide ion must be the base because it's taking the proton and adding it to itself to form water. So what's the acid and what's the base in this reaction? That depends if you're looking at the forward reaction or the reverse reaction. So what you'll see here is that in a reversible Bronsted-Lowry acid-base reaction, you're going to have two sets of things. You're going to have one set where in the reactant side, there's something that accepts a proton and turns into a product. That product in the reverse reaction is going to donate a proton, is going to be an acid. And then there's the other set is reversed. So in the reactant side, for the forward reaction, it's going to be the proton donor. And then it turns into something as a product, which in the reverse reaction becomes the base, the proton acceptor. So usually we distinguish between these two by saying that whatever is the base in the forward reaction is the base. Whatever is the acid in the forward reaction is the acid. And then the acid and base in the reverse reaction we call the conjugate base and the conjugate acid. So the acid in the forward reaction turns into the conjugate base in the products. The base in the forward reaction turns into the conjugate acid. And then you can think about how that would flip going the other direction. So one of the things that you need to be able to do is to find conjugate acid-base pairs when you're looking at a Bronsted-Lowry reaction. And so basically what these are going to be are two substances, one on the product side and one on the reactant side, that differ by only one proton. The acid is going to be something that has one more proton than the base, and that could be the acid has one more proton than the conjugate base, or the conjugate acid has one more proton than the base. The base has one less proton than the acid, so that could be the conjugate base having one less proton than the acid, or the base having one less proton than the conjugate acid. So here's a very famous weak acid, acetic acid, which you might know as vinegar. That is acetic acid in the blue here. So it's going to react with water in aqueous solution, forming acetate and H3O+. Now, the question then is, what's the conjugate base of acetic acid? And so what we're going to do is we're going to look for something that is exactly the same as acetic acid, but missing a proton, because remember the base is going to have one less proton. So here is that pair, and you can see that the hydrogen at the end of acetic acid is what has been donated to our base. So a little aside about notation, you will often hear books refer to the hydronium ion, H3O+. The reason they do this is that a proton is not very stable by itself, and basically what happens when you have a proton in solution is that charge is going to be stabilized by intermolecular forces. In aqueous solution, that happens by the process that we call solvation, where it's kind of like sodium chloride dissociating that we talked about a couple of weeks ago, where the delta minus end of the water will rotate and stabilize the positive charge on the hydrogen ion. So H3O+ makes it sound like that hydrogen ion is bonded to a water, but in reality, that hydrogen ion is actually surrounded by multiple water molecules. So H3O+ is a little bit misleading. Now, in this class, we will use H+ and H3O+ interchangeably. Usually, we'll put H3O+ if we're talking about the conjugate acid of water being a base. And we'll use H plus when we're just talking about concentration. But just know that those things are basically equivalent. Okay, we're going to talk about one more definition of acids and bases. And this is the one that people tend to have a little more trouble with. And so hopefully I can explain why it's useful. So the Lewis definition of acids and bases was developed to explain acid-base chemistry that occurs outside of aqueous solutions. So if you ever get into, for example, ligand chemistry or something like that, you'll talk a lot about Lewis acids and Lewis bases. But the Lewis acid-base definition is also useful to help us identify bases without hydroxide. So you might look at something and say, well, how do I know if something's going to be a proton acceptor for the Bronsted-Lowry definition of acids and bases? So it's useful to know what the Lewis acid-base definition is when you're working with Bronsted-Lowry acids and bases. So Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Now notice that in this definition, what's the acceptor and what's the donor has flipped relative to Bronsted-Lowry, because in Bronsted-Lowry, the acid was the proton donor and the base was the proton acceptor. So Lewis acid, Lewis base is a little backwards in that we're not talking about protons, we're talking about electron pairs. So let's talk about what it means to be an electron pair, acceptor, and donor. So here are two things that serve as Lewis bases. And let's start by looking at ammonia. Remember that ammonia accepts a proton to become NH4+. It's conjugate acid. How does it do that? Well, it's got this electron pair here so that when a proton comes past, that electron pair can serve to bond with the proton. And you can see the same thing happening over here. If you want to turn water into H3O+, there's actually two possible electron pairs that could do that, but I just circled this one, and that could form a bond with hydrogen. So this is why we need to think about electron pairs. So this is helpful when you're looking to see what might be a base. You can say, does this have a non-bonding pair that could bind a proton? So one of the classic reactions between Lewis acids and Lewis bases is the reaction between ammonia and boron tetrafluoride. So in this case, ammonia is the Lewis base because it has that non-bonding pair. And if you think way back to when you did molecular geometries, boron tetrafluoride is one of those weird exceptions to the octet rule in that it has an empty orbital that could be filled. It only has 6 electrons. So the idea behind Lewis acid, Lewis base interactions is that you basically have the non-bonding pair going and glomming on to something that has an open orbital. The previous examples I showed you with a proton, of course the proton has an open orbital because it has no electrons whatsoever. In this case, we actually have other electrons, but we do have one empty orbital, and then that forms a bond. So we've talked about 3 different definitions of acids and bases today. The reason we have 3 different definitions is that each gives us a different insight into how a substance will behave in the presence of other substances. So we have, again, Arrhenius acids produce H+ in solution, bases produce OH-. We have Bronsted-Lowry, where acids are the proton donors and bases are the proton acceptors. And then we have Lewis, where we have acids being the electron pair acceptor and bases being the electron pair donor. I hope this was helpful, and I will see you again soon.